Hello, I'm Steve Reyes from Anritsu Company. A question that often comes up is how long will my VNA calibration be valid? This question can be addressed in a number of different ways, and we have various marketing materials such as app notes, webinars, videos, and white papers that address this topic in more detail. If the question applies to a broadband VNA system performing on-wafer probing measurements, then a different set of factors need to be included. When considering a broadband VNA installation for probing, factors such as the installation of the hardware is an important aspect of it. So you want to make sure that the system is installed optimally in order to enhance the overall VNA stability performance. So in this video, we're going to concentrate on the installation of the VNA hardware and how we can optimize the installation so that we maintain the VNA stability characteristics while performing on-wafer measurement. Later, we can then also explore the different factors that contribute to overall calibration stability. And then finally, we'll take a look at the probing aspects and what things that we can do with the probing part in order to improve overall measurement stability. So here we have the VectorStar 220 GHz broadband system installed on the MPI TS200 probe station, and we're using the MPI brackets that mount the module onto the MP80 positioner. And connected to the modules are the probes, the T220 probes. So we are set up for a probing measurement from 70 kilohertz to 220 gigahertz. Now, many of these points that we'll be discussing will apply to all the broadband systems available for VectorStar, which uses the NLTL, the nonlinear transmission line modules, to upconvert the frequencies to the millimeter wave bands. And so for the case of the different ME7838 systems, we have a 110 gigahertz system, a 125 gigahertz system, a 145 gigahertz system, and then the 220. So by changing these modules, you can determine the upper frequency range of the probing system. Now the key for going up into the broadband millimeter wave frequencies is to optimize the system installation for best performance in terms of raw directivity, stability, etc. And so obviously you would want to eliminate the test port cables from the test port of the module to the probe. So for instance, if we didn't have a direct connect capability like we have here, we would have to mount the modules back on the platen and connect to the probe using cables. And of course, cables in this case will have an impact on the overall stability in terms of temperature and time. So with these modules, we have an interface cable connected going back to the VNA. And there are two parts to the VNA. There's the baseband portion, which is the standard VNA. They can operate up to 20, 40, or 70 gigahertz. And then if you want to go to the higher bands, you connect a test set. And the test set routes the RF and LO signals from the VNA to the module. And so it's the module that upconverts and downconverts the RF and LO signals so that we have the full broadband capability. The lower band from the VNA starts at 70 kilohertz and it goes up to 54 gigahertz, and then it's multiplied up to, in this case, 220 gigahertz. So the stability of the system then is going to be dependent on the cables as they interface from the test set to the module. And so you want to provide support for the cables so that there isn't going to be a lot of flexing after calibration. And that's what we've done here. We have mounted these cable support brackets in order to hold firmly the cables in place and minimize any kind of flexing of the cables after calibration. So with this configuration, without any kind of flexing, the one key aspect of stability is going to then be determined by temperature. The thermal conductivity to the cables will be of importance. So a very important aspect of mounting the Broadband VNA system to a probe station for probing applications is to mount the frequency extension modules directly to the probe. By doing that, you're going to maximize the raw directivity of the entire system. And it's raw directivity that has one of the most important aspects of determining the stability of calibration, especially for on-wafer types of measurements. And so you can review some of the other materials that we provide that discuss that in a little bit more detail. But the key point is, because of the nonlinear transmission line modules are small and compact enough, we're able to mount those modules directly to the probes, whether it's a 110, a 125, 145, or the 220 gigahertz system. That's always been a key objective, is to be able to remove and eliminate the need for test port cables between the probes and the modules. If the modules are too large to mount directly, then what you'll need to do is move the modules back onto the platen and connect to the probe using cables. However, the aspect of the loss will reduce the raw directivity of the system, and also any kind of temperature variation or flexing of the cables, if that might happen, will have an impact on your calibration stability. As far as the rest of the system, so we have the VNA behind the probe station, elevated so that is as close as possible to the chuck, and that allows you to shorten the interface cables to as close or as minimum as possible. So at this time, we could simply land our probes onto a through or a short and evaluate the probing stability over a period of time. And if that probing looks good and stable, then we could move on and perform our measurements. However, if there's some issues that crop up, then we'll want to break down the system and isolate what that problem might be. So for instance, in this case, instead of landing on a through, we could remove the probes and connect shorts to the test ports, and then look at the system in this configuration and determine if there's any drift due to the system in the environment, etc. So that's what we'll do next, and we'll also take a look at the sensitivity of the cables to flexing, which will also give us some indication about the calibration stability over time. As I mentioned, you could connect a short to your test port in order to eliminate factors such as test port cables or probes when evaluating your instrument stability. And so that's what I've done here. I've connected our 220 gigahertz module adapter that goes to a 0.8 connector and connected the 0.8 short from the calibration kit. And so now
port 1 is terminated with a short, and port 2 continues to have the probe mounted. So on our display, we're showing S11 and S22, as well as S21 and S12. Now, the system right now is not calibrated, and you actually don't need a calibration in order to evaluate instrument stability. And so with the calibration not applied, I can take a look at S11 and S22 and evaluate that over time. But of course, the variations will make it a bit more challenging, and it'd be better if I normalize that. So if I want to start zooming in on this, I can first go to my trace menu and reduce the traces down to 2, so that I'm just looking at S11 and S22. And now if I want to normalize, then I of course could go into my display and store the data into memory and do a data divided by memory for the two traces. And so now I have the two traces overlap. And now going from a 15 dB per division display, I can bring that down to 0.1 and now look at my display in terms of stability over time and temperature. And this is giving me an opportunity to evaluate or determine if there is any difference in stability when I have my probes connected and landed on a substrate, for instance, or a DUT, compared to when I just have the test port terminated with a short. So this gives me a nice little comparison and will allow me to determine if my system is stable, but my landings need to be checked a little more carefully. If we wanted to evaluate the system sensitivity to cable flexing, we could take a look at that as well. So in this case, I've removed the cable support mechanism so that I can induce far more flex than I would normally see in my system. In order to normalize this, I'd go to my trace and store the data to memory to get a renormalization. And so now I can move my cables to evaluate. The scaling of this right now is at 0.1 dB per division. And so you can see even with a drastic move, there really isn't strong sensitivity to cable movement, especially when you consider once you mount the cable support brackets, then you're certainly going to minimize that aspect. But it's always a good idea to verify that in your system, just to see how sensitive. It could also be a good opportunity to confirm that all your connections are tight. But you can see even with a full band 70 kilohertz to 220 gigahertz, in this system, we are not overly sensitive. That's primarily due to the fact that we have our test and reference receiver down converters located in the module right up at the test port of the module. And so that minimizes quite a bit of any variations you'll get from cable changes or cable flexing. In addition to evaluating S11 and S22 stability of our broadband systems by connecting a short to the test port of the modules,
We can also evaluate S21 and S12 stability by connecting a through between the modules. So in the case of the 110 and 125 gigahertz system, we can use a 1 millimeter female to female through adapter. For the 145 gigahertz system, we can use the 0.8 millimeter female to female adapter. In the case of the 220 gigahertz system, the 220 gigahertz modules do not provide a threaded test port connector, so we're not able to use a female to female threaded adapter for through measurements. So in that case, we can use the 33GG50 Throughline adapter that's provided with the system. If you recall, the test port of the module provides a UG387 flange adapter, and the pins of that flange is what provides guidance for the coaxial pins and will ensure that they align before making the insertion. And so for the case when we were using the 0.8 short for the S11 and S22 measurements, we were connecting that to the flange adapter going to 0.8 coaxial connection. And so these adapters are available and can be used to convert your 220 gigahertz modules for 110 and 145 gigahertz operation by attaching these coaxial adapters. So now we have this Throughline adapter connected between our modules and are able to perform our S21 and S12 stability over temperature and time. And so now we can take a look at our system performance by monitoring the trace and we start off with a 4-trace display after doing our preset, but I can change that to 2 traces and change the layout in order to have a 2-trace layout for comparison of S21 and S12. Trace 1 is now set for S11, so I'll change that to S21 and change from a Smith chart display to a log, mag, and phase display. And so now trace 1 is S21, log, and phase, and S12 is log, mag, and phase as well. So now we can normalize these traces by storing the data to memory for both traces and scale in our trace to get a better view of both magnitude and phase. And I've reduced these down to 0.1 dB per division for the log and 1 degree for the phase. And I'll do that for both traces, and that will give us an opportunity to evaluate the system over time and as well over temperature. So keep in mind that we are evaluating this system now because of that through adapter over the complete range from 70 kilohertz to 220 gigahertz, but without the probes attached, which gives us a good opportunity to evaluate the system without including any kind of drift that might be induced by the probes or the touchdowns. And so this will give us a good example of system performance and an opportunity to determine that the system is operating as we would expect. So then the next step would be to add the probes to this system and touch down and then evaluate over time and temperature as well. Also, you want to keep in mind that if there is a wide variation in the temperature in your lab overnight, for instance, and you're running your stability tests overnight, you want to keep that in mind because the temperature variation is what's going to affect the overall system stability. And so sometimes it might be a better approach to evaluate that during the time when the temperature of the lab is more stable.
In this video, we focus on the hardware aspects when evaluating measurement stability of a VNA broadband system. One of the first things to consider is removing the probes from the test port of the frequency extension modules and attaching coaxial shorts and throughs on the test ports of those modules in order to perform the evaluation and eliminate the effects of probes, positioners, and probe landings. Another important part of the evaluation is to consider the temperature variations in the lab. So you'd want to perform this evaluation during a time when the temperature of the lab is reasonably stable. Cable movement, especially on the test port cables from the VNAs to the modules, is something to consider as well. So you want to minimize movement after calibration of the test port cables, the interface cables between the VNA and the modules, in order to minimize any kind of movement over a period of time after calibration. However, we did find that because of the nonlinear transmission line location of the test and reference samplers very close to the test port, the effects of interface cable movement is pretty minimal. However, it's still a good idea to use some sort of support mechanism of the cables in order to ensure that the cables do not move after calibration. Once you've established the measurement stability of the hardware without the probes, you can then attach the probes and evaluate during the probe landings. When you do your installation, remember to eliminate the need for test port cables between the module and the probes. And of course, because of the nonlinear transmission line modules being so small, we're able to connect directly to the probes and eliminate the need for the test port cables between the modules and the probes in order to maximize raw directivity performance. And as we saw, the raw directivity is a key contributor to overall calibration stability. So I hope that the video was useful in exploring some of the aspects of evaluating measurement stability of a broadband system. Subsequent videos will talk more about the calibration aspects as well as probe landings. So for more information on the VectorStar VNA systems, please visit us at anritsu.com, and thank you for your attention.